and what it tells us about a function. So the first part of this lesson is me explaining what's going on, and then we'll get into some practice. Our goals here are to understand the nature of the second derivative as it relates to the shape of the graph. And the second derivative is going to tell us something about concavity. Now, Zach, and I don't know if Nicole, you did this. I think it might have been Zach and Demi. When you did the max-min problem, you used what's called the second derivative test. Do you remember that? That I had asked you if somebody had taught you the second derivative test, Zach, and you said yes. I want you to make a note here that if you do go back and look at the second derivative test, that is not what this is. The second derivative test, which is what you used in your max-min problem, is something different. And for everybody else, we are going to learn the second derivative test, which is not this, later. I think tomorrow. The second derivative of a function tells us something about the shape of the function, and that shape is referred to as concavity. So what we're going to do is determine second derivatives or use second derivatives to find out where a function has a particular type of concavity. And it's going to lead us to coordinates of inflection points. So a little bit of background here. This is review. What does this say? It says when the derivative of a function is positive, the function is increasing. And I want to break this down here. I don't have to use the word function. I could use anything. When the derivative of y is positive, y is increasing. When the derivative of position is positive, position is increasing. So whenever the derivative of a quantity is positive, that quantity is increasing. The opposite of that is if the derivative of a function is negative, then the function is decreasing. And for all of this that I have on the screen right now, just replace the word function with y. And it should start to make sense, because if the derivative is positive, y is increasing, it has a positive slope. Well, what that means, and this is where things get a little bit more challenging for your brain to latch onto, is that if the derivative of the function tells us what the function is doing, then the second derivative tells us what the derivative is doing. Because the second derivative of a function is the derivative of the function. The second derivative, well, let me write this out. The first derivative tells us what y is doing. It's the derivative of y, so it's telling us what y is doing. The second derivative is the derivative with respect to x of the first derivative. So it tells us what the first derivative is doing. Whatever you are taking the derivative of is the thing that tells us that the derivative of that thing tells us what's happening to it. That was a really tortured way of saying it. The derivative of the quantity is going to be a new quantity called the derivative that tells you what's happening to the original quantity. Does that make sense? So the derivative of the derivative is telling you what the derivative of the function is doing. You got to really think hard on that to wrap your head around it. The third derivative would be telling us what the second derivative is doing. So where does this leave us? It leaves us with this idea. The second derivative of a function tells us what the slope of the function is doing. Remember, the second derivative, which is the bottom line on your screen here, is telling you what the first derivative is doing. Well, this is the slope. So the second derivative of a function is telling us what the slope is doing, which is weird. Yeah.
Can we think of it as, sorry, I lost my words.
That's okay.
Like rate of change. Like, so the first derivative is the rate of change of the function, and the second derivative is the rate of change of the rate of change.
Yes, definitely. In case that didn't come through on audio, what Evan's saying is, can we say that the second derivative, since the first derivative is the rate of change of the function, can we say that the second derivative is the rate of change of the rate of change of the function? Yes, definitely. As it pertains to the shape of the graph, I can't wrap my head around that. But it is true, definitely. I'm going to think about how that interpretation would pertain to the slope, because I think I can use that in the next lesson, the next time I teach this. Let's get specific now here. If the second derivative of a function is positive over an interval, that means going from left to right, the slope of the function is increasing. Now, what does it look like when the slope of the function is increasing, or when the rate of change of the when the rate of change of the function is increasing? What does that look like? Well, first of all, we call it concave up. And it's called concave up because it has a concave up shape. If the second derivative is positive, then the first derivative is increasing, which means the slope is increasing, or the rate of change of y is increasing. But it's going to look like that. Now, I suspect that if I asked you, everybody in the room, to sketch a curve where the slope is increasing, I suspect that many of you would do something like what I've got drawn there. You would say, well, it's getting steeper and steeper and steeper. And you wouldn't include the other part. And I think some of you might look at the left-hand part of that curve I've drawn and say to yourself, isn't the slope decreasing there? But the slope is increasing, and let me demonstrate that to you. And this isn't in your notes. This is just a cheapo animation I put together by creating a bunch of pages. If I were to take a look at particular points on this graph that I've got in your notes, and I look at a hypothetical slope, I don't think it would be unreasonable for you to estimate that the slope of the tangent at point A is -3, would it? Does that seem like a reasonable slope? And if I were to look at the slope at a different point, say B, I think you would agree that it's still negative, but the magnitude of the slope is not as great. It might be -2. And we know, of course, that at point C, it would be even shallower, but still negative. And at point D, it would be a horizontal tangent, so the slope would be 0. Then it might be 0.5, then it might be 0.8. Do you get my drift here? These are 6 hypothetical slopes. Well, when you go from a value of -3 to 2, that's an increase. You know, this is high school math. We have to imagine numbers existing, whether they're positive or negative, and they exist on a number line. And when you look at going from -3 on a number line to -2, you're increasing, you're adding something. From -2 to -0.5 is an increase. That's an increase. That's an increase. These are all increases. So as long as the curve has this shape, a shape that if you put that shape out in the rain, it would fill up with water, it's called concave up, and it's because the second derivative is positive. Does anybody have any questions with that page that you're looking at right now? All right. Well, the opposite is true. If the second derivative of the function is negative, then the slope of the function must be decreasing in that region. And we call that concave down. And it looks like that in general. I mean, the exact shape depends on the function, but it's going to have that overall shape. And again, if we take some points and look at hypothetical slopes, the slope of the tangent there would be 3 maybe, then it would be 2.5, then it might be 1.5, 0, -1/2, -0.8. But as you go left to right from point to point, the slope value decreases. So the second derivative is negative. By the way, it's very easy for you to remember which is which with regards to the second derivative, because if I have, say, this shape, this is concave down. This is concave up. The second derivative is negative. The second derivative is positive. And if you have to, I haven't run into too many people that need to resort to some kind of mnemonic device or memory aid, but when you have people that are negative, generally speaking, they walk around with a frown on their face. Right? When you have people that are positive, generally speaking, I mean, you can't smile all day. It gets exhausting sometimes, but positive people smile. And if you look at the shape of their mouth, that tells you whether they're positive or negative. That tells you whether the second derivative is positive or negative. Okay. Now, what's an inflection point? When you did polynomial functions in Math 30, and even if you're in Math 30 right now, you did that already, you knew that inflection points existed when the graph of the polynomial went through the x-axis with what I called a twist. But really, there's a better definition. It's a more mathematical definition. It's where the concavity changes. It's where the concavity goes from, if I look at my diagram here, from a negative concavity to a positive concavity. It changes about, I'm going to say it changes about there, and I'm going to make the dot really big so that I cover my bases. That immediately to the left of that dot, you have a downward concavity, and immediately to the right, you have an upward concavity. So the concavity is changing. The second derivative is changing from negative to positive. And that's the definition of an inflection point. So think about this for a second. It's a little slippery, but if it goes from a positive to a negative concavity or vice versa, that means at that instant, there's no concavity. It's neither concave up nor concave down because it's switching at that instant. And since concave up is because the second derivative is positive, and concave down is because the second derivative is negative, then at the inflection point, since it's neither concavity, the second derivative there is not positive and it's not negative. I'm not saying it's zero. It might be. I'm saying it's not positive and it's not negative. What are the only other possibilities that a number could be? It could be positive, it could be negative, it could be zero. What else could it be? I shouldn't say number. The derivative could be undefined. And where I'm going with this is that at these inflection points, a second derivative is not positive or not negative. That's it, which means it could be anything else. It could be zero or it could be undefined. And at any point of inflection, the second derivative will be equal to zero or it will not be defined, one or the other. Much like at max-min points, the first derivative is either zero or undefined. But, and I know this is a lot to follow, but I also know that you're all really intelligent. When you look at a first derivative being not defined or zero, does every one of those points where the first derivative is not defined or is zero, is every one of those points necessarily a max-min? No. That's what we do a first derivative chart for. The same thing is going to be true here. These points are called critical values, and I want to just check something here. Do you have the second derivative in your handout in this part of your notes? Okay. I have to transpose this into Notebook, and sometimes I miss a beat. These points where the second derivative is either equal to 0 or is undefined may not actually be inflection points. These points are called the critical points of the second derivative, just like the points where the first derivative is equal to 0 or is undefined are critical points of the first derivative. And these points are points that we are suspicious of being inflection points. In order for us to determine if they truly are, we need to do a second derivative chart. We need to identify those critical values of the second derivative, complete a chart to find out where it's concave up and where it's concave down. So before we get to the first example, does anybody have any comments or questions about anything I've discussed with you so far? Okay. So example 1 asks us to determine all of the pertinent features of the graph so we can construct the graph, and I would like you to take a minute and write down what the first and second derivatives of this function are, because we're not going to spend class time today finding them. If we did, we'd be here for hours. So what are the pertinent features? Symmetry. Is it symmetrical or not? If it is symmetrical, is it odd or even? What's the x-intercept or x-intercepts if there are any? What's the y-intercept if there is one? Are there any asymptotes, vertical and horizontal? Are there any max-min? And now, are there any inflection points? So let's start off with the intercepts. The x-intercept will be 0 because, again, if we want this whole thing to be equal to 0, which is what an x-intercept is, the numerator has to be 0, so x equals 0. In other words, when you find x-intercepts, you look at the top. The y-intercept is always found by changing x to 0. If we put 0 in for x, you're going to get 0, another of the many functions that happen to go through the origin. But those are the only intercepts. If we look at the asymptotes, there are no vertical asymptotes because the denominator of this expression can never be 0. In other words, there's no non-permissible values of x, so there's no vertical asymptote. The horizontal asymptote will be at y equals the limit as x approaches infinity of that function. But do you see my point that I was driving at earlier? And I do appreciate that not all of you have taken Math 30-1 yet, but this will be the third or the fourth time I've given you this rule. That if the degree on the top is smaller than the degree on the bottom, you will have a horizontal asymptote on the x-axis. If you choose to, and I'm just being a little lazy here, but if you choose to divide everything by x squared and then look at the behavior of that at infinity, the top of this will be 1 over x, which becomes 0 at infinity. The bottom will become 1 plus 1 over x squared, which becomes 1 plus 0 at infinity. You get 0 over 1. Just for kicks, is it odd or even? Or neither? Well, here for the symmetry, we would put in negative x for x, and simplify this to get negative x over x squared plus 1, which is exactly negative 1 times the original function. We could take this negative in front of the x and put it in front to demonstrate that f of negative x is negative f of positive x, which means it's odd. So we've got all of the information about I call this just kind of the garnish of the whole graph. These are the little tiny features that are going to help in graphing it. But the heart of the matter is going to be found by doing a first and second derivative chart. So your first derivative, let me rewrite it for you. Your first derivative is x squared minus 1, I think. No, 1 minus x squared over x squared plus 1, quantity squared. So what do we have for critical values of x? The only critical values of x for the first derivative are 1 and negative 1. And I didn't choose to write it down this way or ask you to write it down this way, but you should know that 1 minus x squared is 1 plus x, 1 minus x. That's where I'm getting the two critical values of x from. And that means that my first derivative table, I should have said, I hope you're organizing your work well here, because there's a lot that you have to write down, right? Our first derivative table will go from negative infinity to negative 1, from negative 1 to positive 1, and from positive 1 to infinity. And across the top, we can have 1 plus x, 1 minus x, and x squared plus 1 squared. If you're feeling adventurous, everybody, you know, all we really care about is this column. I've never told you this before. I think it's maybe a mistake for most people. But if you want to, you could just physically put in a number for x in the first interval, put it into the whole derivative and see if you get a positive or negative. The purpose of doing a chart or a table is for you to kind of break it down into simpler pieces and methodically get the answer. This is negative, positive, positive. This is positive, positive, negative. Be very careful here. Because 1 minus x has a coefficient in front of the x that's negative, so it doesn't go from negative to positive, it goes the other way. And I think in a case like this where even the 1 plus x is written backwards, it maybe serves your needs better by just putting in numbers. It only takes a second. Would we agree on the signs, so the population of that part of the chart? Okay. When I look at x squared plus 1 quantity squared, since I'm squaring x squared plus 1, and it doesn't matter what's inside, I'm squaring the whole thing, it will be positive. And what that means is the first derivative is negative, then it's positive, then it's negative. That tells us y is decreasing, then increasing, then decreasing. That tells us we have a minimum at negative 1, and we have a maximum at positive 1. And we might as well find the y coordinate right now. I'll just write up here what the original function was, and I need you to confirm that my memory is right. This is the original function. So you need to put 1 in, and you need to put negative 1 in. When you put 1 in, you get 1/2. When you put negative 1 in, you get negative 1/2. No surprise that these are opposite because the function is odd, right? You get the opposite y coordinate for the opposite x coordinate. Any questions about finding the max min? Now we need to do inflection points, so we need to look at the second derivative. And the second derivative is 2x times x squared minus 3 over x squared plus 1 cubed. Did I remember it right from the previous page? All right. So what kind of critical values of x do I have for this beast? I have plus or minus the square root of 3, because x squared minus 3 is not allowed to be 0. Well, it is allowed to be 0, but when it's 0, it makes the second derivative 0. Also, there's another value of x that makes the second derivative 0, and that's 0 because of the 2x. The denominator doesn't have any zeros, so we're done. So our second derivative table will go from negative infinity to negative root 3, from negative root 3 to positive root 3, from positive root 3, from negative root 3 to 0, from 0 to root 3, and from root 3 to infinity. I knew I was missing a critical number when I was writing those out and saying them, because I was starting to count the intervals I would get, and I knew since there were 3 critical numbers, I have to get 4 intervals, and I was going to come up short. Across the top, 2x, x squared minus 3, x squared plus 1 cubed. So a little bit more thought here. The 2x will be negative, negative, positive, positive. I'm just going to throw this idea out and find out how many of you would potentially do it. That x squared minus 3 is not a linear factor. So it's not going to go from negative to positive or positive to negative. It's probably going to go from positive to positive or the other way around. How many of you would consider writing that x squared minus 3 as x plus root 3 and x minus root 3? And that will work for you. Okay? Then you'll just have an extra column. For those of us that don't want to do that, my advice is to literally take a number in this first interval and square it and subtract 3. And I hope that many of you don't actually need to do that on the calculator. You're going to see you get positive. If I take negative 10 gajillion and I square it, I get a positive big number. Minus 3, you get positive. The other option here, and I think, Evan, you brought this up one time. It might have even been in Math 20 when we did inequalities. That since x squared minus 3 can be thought of as a parabola that opens up, it has to go from positive to negative back up to positive. And it has to do so past the 2 zeros, past the 2 x-intercepts. That might work too. But what you're going to discover is you will get positive between negative infinity and negative root 3, negative in the next 2 intervals. And this is just the way my mind works. I know that if I take a number, say in this interval between 0 and root 3, when I square it, I'll get a number less than 3. And when I subtract 3, it will become negative. The last one is positive everywhere, and it's got nothing to do with the exponent of 3. It's got to do with the fact that this is x squared plus 1. Doesn't matter what x is, you're going to square it, it's going to become positive, then you're going to add 1, it will be positive still. So d2y dx squared is negative, positive, negative, positive. So y is concave down, concave up, concave down, concave up. It isn't that y is increasing, because it's the second derivative. What's increasing or decreasing is the first derivative, which is the slope. What does that tell us? That tells us that there's an inflection point here. There's an inflection point here. And there's an inflection point here. So before we finally put all of this together, everyone, we have to find the y coordinates of these inflection points. And again, our function was y equals x over x squared minus 1. No. X squared plus 1. Okay. So you put in, well, I put in 0 and I get 0. We know it goes through the origin. What does that mean? Okay. There will be an inflection point at the origin. As the graph goes through the origin, it's going to change from being concave up to being concave down. It's going to have this shape, everyone, that I'm showing you with my hands. As it goes through the origin, it's going to go from concave up to concave down. It's got to have that kind of twist to it. When I put in negative root 3, let's see. Negative root 3 squared is 3. 3 plus 1 is 4. So I get negative root 3 over 4. And I get positive root 3 over 4 here. Now comes the challenging part of putting it all together without cheating and looking at your graphing calculator. So let's scale our x-axis so that it includes all of the critical values of x for either the first or the second derivative and goes a little bit further. I think the biggest critical value of x we had was negative root 3, wasn't it? And positive root 3. Is root 3 1.73 something? Okay, so let's scale this. Let's scale this to 3, I think, is sufficient. And it doesn't have to be perfect. And to negative 3 in the opposite direction. Now, didn't we have max and min values? Were they 1/2? So when you look back at your first derivative chart, we have on there the coordinates of the max and the min. If my memory is right, we had a min at negative 1, comma, negative 1/2. Okay, so, and the critical values or the x coordinates, no, the y coordinate for the inflection point was negative root 3 over 4. So can somebody crunch that number, negative root 3 over 4, and see if you get about 0.42 or 0.43? Okay, so vertically speaking, the biggest important value of y is 1/2, and the smallest is negative 1/2. So I think if we do this, this is 1. And this is negative 1. I think that'll do the trick. So let's put in the points first. We know that the graph goes through the origin, right? We know that the graph has a maximum at 1. I'm going by memory here, so I need your help. It has a maximum at 1, 1/2. So I can put that in. Here's 1/2. It has a maximum here. It has a minimum at negative 1, negative 1/2. There's that odd symmetry looking at those 3 points. Let's throw in our asymptote. I believe, if memory serves, the x-axis was an asymptote. Yes? Okay. Now across the top, I'm going to put, this is going to be interesting, I'm going to put all of my critical values of x for the derivative, which were negative 1, 0, and 1. Am I correct? This top is just a guide. It's not an axis or anything. It's just a number line. So I really want to make sure the first derivative had only, was 0 a critical point? It wasn't. Only 1 and -1, correct? So that means that we look at the first derivative and we see, correct me if I'm wrong, but in the interval from -infinity to -1, it was decreasing. Then it was increasing everywhere up to there, and then it was decreasing afterwards. You with me? Now, we're going to put on the same number line the critical values of x for the second derivative. And that was -√3, which is -1.7 approximately. So we have a critical value for the second derivative at -1.7. We have a critical value of the second derivative of 0. And we have a second derivative critical value of +√3. Were those the only three for the second derivative? Okay. Now, when you look at your second derivative table from -infinity up to -√3, it's concave down. Then it's concave up to 0. It's concave down after 0. And then it's concave up after √3. I want to point something out to you, and I don't know that it's that big of a deal, but I like it. If you look at when I drew those concave up and down arcs, when I got to a point here, which was a critical value of the first derivative, I intentionally put an arc right over top of the whole thing, because that critical value that I'm pointing at has nothing to do with concavity. Similarly, over here, this critical value is for the second derivative, but look how I drew the up arrow. It's over top of that because that critical value has nothing to do with increasing and decreasing. I'm going to give everybody a minute here. Oh, and we also have inflection points, don't we? We have an inflection point at -√3, comma, -√3 over 4. And -√3 over 4 is approximately 0.42. -0.43. So over here at I'm looking here at -√3, I have an inflection point at negative about 0.43. This point should be up maybe a little bit, but it doesn't matter. So I have an inflection point about here. And then I have another inflection point, and I will even put IP here. I have another inflection point at +√3, comma, -0.43. And I'm going to put inflection point here. I'm going to write min here, max here, and this is also an inflection point. So I'm going to give you a minute here or two to see if you can come up with what the graph would look like. You have to stay within the confines of everything at the top of the page. By the way, before I forget, this has been here for about a week. Whose is this? It's yours? Okay. There you go. I know that it's tempting to grab your graphing calculator, but I wouldn't be doing right by you by saying, oh, just look on your graphing calculator. How many of you have it? And it was pretty much not obvious, but required a bit of thought, but you got it figured out in short time. I mean, you have to understand as well that it's an asymptotic nature towards infinity and negative infinity. So in my head, I'm just going to draw some stuff here. If this is a max, this is a sketch. I haven't committed myself to anything. It's like I'm an artist and I'm sketching stuff and then I'm going to fix it. It's got to look like this here. It has to look like that there because that's a max. And it's got to look like this here. But it also has to have this shape over here. And if you look up top, that certainly explains why it's concave down up to that point. And then if it's going to go from this shape to this shape, it's got to change as it goes through the origin. And then the other side is going to look like that. And that's a very rough sketch, but you know what? It's pretty good. I'm not even going to clean it up, all those little errors in terms of the graph not being a perfect line. I'm just going to leave it. That's what the graph looks like. So you understand that, I hope, you know, this was just me roughly sketching. This is what the graph looks like. And if you were to use your graphing calculator now with the same window settings, let's see how we did, or how I did, I suppose. What do we have? We have y equals x over x squared plus 1. My window settings, I went from about -4 to 4 in terms of what I drew. I went from about, well, I'll just go -1 to 1. It's pretty good. I was maybe a little too severe in terms of how close I went towards the horizontal asymptote, but it looks pretty good. And it's odd. You can see it's odd. Any questions with that example? All right, here's where we're going to end it. And this is what I want you to do for tomorrow. You can write down these two derivatives, the first derivative and the second derivative. And what I want you to do tomorrow, and you have to be honest with yourself. If you want to cheat, cheat. But you're cheating yourself. I want you to see if you can complete this example up to the end. Coming up with a sketch of this graph, try without using your graphing calculator. And I know it's going to be really tempting at times. But this is kind of the big league here. This is a calculus class. While you're writing them down, I'm going to just make sure that they are correct, because that would certainly be an unkind move on my part if I gave you the wrong derivative. The derivative of x to the third times x plus 3 to the 2/3 is x plus 1 over x to the 2/3, x plus 3 to the third. And the derivative of that, 1 plus x over x to the 2/3 times x plus 3 to the 1/3 is -2 x to the 5/3 times 3 over x to the 5/3 and also over 3 plus x to the 4/3. So that's your assignment. I really, this isn't, quote, practice, try it if you want. I want you to work through and see if you can complete this for tomorrow. And that's it. What this means, since we're going to be spending, well, I don't know, we might be able to do the next lesson tomorrow, but I would rather just have a practice day, is that your exam, which I've said was the 26th, is probably going to be the 27th now. But I would rather have quality over rush, being rushed through all this stuff. And Zach and Nicole, just checking here. I'm assuming Demi is not there today. Thank you. While you are working, I'm just going to be working up here. I'm not going to be talking or instructing. I'm just going to be working on this and starting with all the preliminary stuff like intercepts, asymptotes, symmetry, that kind of stuff. That way, at least you can check your work while you're still in class. Those are the conclusions that I came to. No symmetry. We have two x-intercepts, 0 and -3. Because we have a factor of x to the third, x equals 0 is an x-intercept, and the x plus 3 gives another x-intercept. Y-intercept is 0. You simply put in 0 for x. There are no asymptotes. It's not a rational function. I want to be careful there because there are other functions, as you know from Math 30-1, like exponential and logarithmic, that have asymptotes. But we haven't studied those in this course yet, so we will. But basically, it's not a rational function, so there's no asymptotes. Another way to look at that is to say that the domain is all real numbers, so all values of x are permissible. And then on the side, I simply put the critical values of x for the derivative and the critical values of x for the second derivative, which you need to do your two charts to find your intervals of increase and decrease with the first derivative and intervals of upward and downward concavity with your second derivative. So I'm going to end it there, and you have a little less than 10 minutes to see what you can do with that and finish the rest for homework.